Class 11th Chemistry, we were discussing Unit 9 Hydrogen, and in this video we are going to discuss about hydrides. First of all, what are hydrides? Binary compounds of hydrogen with other elements are called hydrides. Binary compound means compounds which are made up of two elements. Actually, almost all the elements of periodic table can react with the hydrogen except noble gases. Okay, and these binary compounds of hydrogen with other elements are known as hydrides. If E is the symbol of an element, then hydride can be expressed as EHX, for example, magnesium hydride MgH2, or EMHN, for example, B2H6, that is diborane. The hydrides are classified into three categories. First category, ionic or saline or salt-like hydride. Second category, covalent or molecular hydrides. Third category, metallic or non-stoichiometric hydrides. First of all, ionic or saline hydrides. These are stoichiometric compounds. First of all, what is the meaning of these stoichiometric compounds? Stoichiometric compound has an exact and fixed composition with a small integer ratio among its atomic components. It means if constituent elements are present in exact and fixed ratio, then these compounds are known as stoichiometric compounds. So we can say ionic or saline hydrides are the stoichiometric compounds of dihydrogen formed with most of the S block elements, which are highly electropositive in character. Lighter metal hydrides such as lithium hydride LiH, beryllium hydride BeH2, magnesium hydride MgH2 have significant covalent characters. BeH2 and MgH2, these are polymeric in nature. Now this is the structure of BeH2. It shows the polymeric nature of BeH2. That is, many BeH2 units are linked to each other. The ionic hydrides are crystalline, non-volatile and non-conducting in solid state. However, their melts conduct electricity and on electrolysis liberate dihydrogen gas at anode, which confirms the existence of H-, that is hydride ion. Actually, hydrogen gas is liberated at anode, and as we know, anode is positively charged in this electrolytic cell. So this confirms that negatively charged H- ion discharge at the anode and liberate hydrogen gas. Okay. Saline hydrides react violently with water, producing dihydrogen gas. Like the reaction is NaH, when react with H2O, it will form NaOH and this hydrogen gas is liberated. Lithium hydride is rather unreactive at moderate temperatures with O2 or Cl2, so it is used in the synthesis of other useful hydrides. For example, when lithium hydride react with the aluminum chloride, that is, this is the dimer of aluminum chloride, it will form lithium aluminum hydride. This is the very useful reducing agent in organic chemistry. In the same way, when lithium hydride react with the diborane B2H6, it will produce lithium borohydride. Again, this is used as a reducing agent in organic synthesis. Next one is covalent or molecular hydride. Dihydrogen forms molecular compounds with most of the p block elements, or simply hydride forms with the p block elements are known as covalent or molecular hydride. Most familiar examples are like CH4 methane, NH3 ammonia, H2O water, HF hydrogen fluoride. For convenience, hydrogen compounds of known metals have also been considered as hydride. Actually, in this case, hydrogen is not present as H- because these are the covalent compound. But for the sake of easiness, these are known as hydrides. Being covalent, they are volatile compounds. Molecular hydrides are further classified according to the relative number of electrons and bonds in their Lewis structure into three categories: electron deficient, electron precise, and electron rich hydrides. First come to electron deficient hydride. It has less few electrons for writing its conventional Lewis structure. Actually, to write the Lewis structure, writing of Lewis structure based on the octet rule. But These hydrides will not follow the octet rule. The central atom in these hydrides have less electron than octet. For example, B2H6. This is diborane. In fact, all elements of group 13 will form electron deficient compounds. Okay. Now, when these are electron deficient, they can accept a pair of electron and they act as Lewis acids, that is electron acceptors. Second category of covalent or molecular hydride is electron precise. Electron precise compounds have the required number of electrons to write their conventional Lewis structure. All elements of group 14 form such compounds like methane CH4 having the tetrahedral geometry. Third category is electron-rich hydrides. Electron-rich hydrides have excess electrons which are present as lone pairs. Elements of group 15 to 17 form such compounds like NH3. It has one lone pair of electron. H2O. In this case, oxygen have two lone pair of electron. HF have three lone pair of electrons. And when they have the extra electrons, lone pair of electrons, so these electron pair can be donated to the electron deficient species and they behave as Lewis bases, that is electron donors. Now, third category, metallic or non-stoichiometric or interstitial hydrides. These are formed by many D block and F block elements. However, the metals of group 7, 8 and 9 do not form hydrides. That's why these group 7, 8 and 9, this gap is regarded as a hydride gap. Even from group 6, only chromium can form chromium hydride, CrH. These hydrides conduct heat and electricity, though not as efficiently as their parent metals do. Unlike saline hydrides, they are almost always non-stoichiometric, just opposite to the stoichiometry, because they are not having the fixed composition. Okay, and being deficient in hydrogen. For example, like this LaH 2.87. Okay, this is not fixed composition and not in the simple ratio. YbH 2.55, TiH 1.5 to 1.8. ZrH, now in this case H may be 1.3 to 1.75. Vanadium hydride may be 0.56. In the same way this. Okay, so these are non-stoichiometric hydrides. In such hydrides, the law of constant composition does not hold good. Some of the metals like palladium and platinum can accommodate a very large volume of hydrogen and therefore can be used as its storage media. Simply we can say hydrides of palladium and platinum, these are used as a storage media. This property has high potential for hydrogen storage and as a source of energy. Now problem 9.2. Would you expect the hydrides of nitrogen, oxygen and fluorine to have lower boiling points than the hydrides of their subsequent group members? Give reasons. On the basis of molecular masses of NH3, H2O and HF in their respective group, these have the lowest molecular mass. So their boiling points are expected to be lower than those of the subsequent group member hydrides. Clear? Because in these hydrides, these are the covalent hydrides, covalent molecules. So the van der Waals force is existing between these molecules. Van der Waals force depends on the molecular mass. Higher the molecular mass, higher the magnitude of van der Waals force. Okay. According to this, these NH3, H2 and HF must have the lower boiling points. Okay, but due to higher electronegativity of nitrogen, oxygen and fluorine, there is intermolecular hydrogen bonding in their hydrides. Hence, the boiling points of NH3, H2O and HF will be higher than the hydrides of their subsequent group members. Is it clear? Due to the presence of intermolecular hydrogen bonding, their hydrides are more. Sorry, their boiling points are more. Problem 9.3. Can phosphorus with outer electronic configuration 3s2 3p3 form pH5? Answer is, although phosphorus exhibits +3 and +5 oxidation states, but it cannot form pH5. Why? Because of high enthalpy of atomization value of dihydrogen and high electron gain enthalpy value of hydrogen do not favor to exhibit the highest oxidation state of phosphorus with hydrogen, and consequently it will not form pH 5. Okay, thank you.